One. Hello. Hi, ast111, and we are here for our first Google Hangout. And so I'm Frank.
I'm Bill.
Hi, I'm Teresa.
And we'll start off a little bit about what it is we do or like to do in astronomy. Let's see. So what do I like to do? I like stars in general. I'm particularly fond of blowing them up and all the consequences that come out of that. So I'm a professor at ASU. I'm that funny guy, or not so funny guy, as the case may be, on the videos that you're watching for the course. And there I go. So, Bill, what do you do?
So I'm a postdoctoral researcher, so I also study stars, so I get to do what Frank does, except for I don't have to teach classes or a lot of the other administrative stuff, so it's a lot of fun. I deal with white dwarfs. You wish, Frank. So I study a lot white dwarf stars, which are sort of the remnants of older stars. The sun will turn into one, something that's roughly the size of Earth, but the mass of the sun. And I study what happens when you put material back on them, and it can have interesting explosions known as novae, or even other types of explosions. You might have heard of a type 1A supernova. So a lot of overlapping with Frank's research.
Hi, I'm Teresa again. What my research is kind of different is I'm more observational astronomer, and I study faraway galaxies. So you might have seen in the past press releases from like the Hubble Space Telescope and other telescopes of really distant, these what we call deep fields, where we take telescopes and stare at a part of the sky for hours and hours and hours, and we can see in these parts of the sky thousands of galaxies. And I study how these galaxies evolve with time.
Hey, Teresa, I see there's some funny green symbols behind you there. So you can't be too much of an observer, because I see funny squiggly symbols.
Oh, yeah. Well, you definitely have to do computational stuff no matter what you do.
There you go. Cool. Okay. So generally what we're going to do is we're going to walk through some of the questions that people asked on the discussion board. If you want to ask a question while we're going here, feel free to post stuff on the YouTube thread there, and we'll pick up the questions as we go along. Then we'll sort of morph into current events. There's some cool stuff coming up. We can talk about some cool stuff going on. And then on time permitting, we may have a few little presentations to talk about some stuff in astronomy. So, Bill, you want to start off? You want to take one?
Sure. So one of the questions that we had today was how to tell if the Earth is a sphere, not flat. Simplest solution possible. I like how quick that question is. Very pithy. So there's a number of ways you could do this, and one's kind of relevant upcoming here. We have towards the end of the month, was it January 31st we were talking? I actually can't remember the date. But we have the full moon, which happens to also be a blue moon, which just means it's the second full moon of the month. It's also a supermoon, meaning that the moon is closest to Earth, meaning it is just a little bit bigger in the sky. It's actually not super dramatic. And then also, finally, it'll be a lunar eclipse. And it's this last thing, the lunar eclipse, when the Earth passes directly between the sun and the moon, that we can actually use as an argument to prove that the Earth is round. This is because as the Earth passes in front of the moon, we see the shadow of the Earth, and it actually appears as first a crescent, and then eventually basically a full circle that blocks out the moon. If the Earth were simply flat, you can find some humorous images of this where the shadow would look more like a straight line or some weird representation of a flat Earth, and the only way it would work is if the Earth were a completely round disk, and that seems a little bit unlikely, and that disk is perfectly aligned with the sun and the moon, and it just makes more sense that it's probably a sphere for the Earth. But another technique, I believe that one was used by Aristotle to explain that the Earth was probably round. But then there's actually another method that was used by the Greek, I don't know, I'd say scientist Eratosthenes, where you can put, say just sticks in the ground or a flagpole or something at different latitudes of the Earth, and look at the same time of day, perhaps say when the sun is highest in the sky, and measure how long these shadows are. And depending on where you are on the Earth, the different curvature you're at, these shadows will have different lengths. And this was actually used to approximate the circumference of the Earth thousands of years ago, before we had, telescopes and a lot of other modern equipment. But that's something else, that with a flat Earth, all the shadows should be the same length and the same angle at the same time of day. But if you have a curved Earth, these shadows are at different angles. So those are two fairly simple ways you can prove it without having to get in a spaceship and go around and see that the Earth is round.
Yeah, actually, I'll pick up part of that question. Flat being the simplest possible solution. Actually, flat is probably the most complicated solution you could imagine, because you have to arrange so many things to be just right, and even then it still doesn't work. But yeah, I would say in general in astronomy, astronomy sort of comes in a couple of shapes. One is sort of spheroids, so not quite spherical, and then sort of disc-like, usually because there's some fair amount of rotation involved, and sometimes that rotation makes pretty spiral galaxies and stuff like that. But kind of spheres and discs. But flat planes, no, not really. That's not the natural shape of things. And as we will see later on in this course, once you get above about 200 kilometers in mass, gravity wins. It will deform rock and it makes a sphere. And that's why generally about 200 kilometers in size, things look pretty spherical, because gravity can bend rock at that point. So, yeah. Oh yeah, and hey, if you're paying attention, you have a homework problem this week involving some cities of Joy and Bar. And if you're paying attention to Bill's story, you might be able to make a connection between that homework problem and what was done to measure the size of the Earth. So, Teresa, you want to take one?
What do we have?
Okay. How about the background radiation? Why is the background radiation the temperature it is?
Oh, so if we go back to the Big Bang, whatever, 13.6 billion years ago or so, when it occurred, all the temperature of the light was the same, and then as we now know that the universe is expanding, and as that expansion occurs, the wavelength of light, of that energy light, it actually gets stretched out with time. And so basically there's this glow from the remnant of the Big Bang that's in the microwave wavelength now. That's why we call it the cosmic microwave background. That we can see this glow, and as the universe continues expanding, that actually the wavelengths will get stretched out further, become redder light, cooler temperatures, and keep cooling off.
Cool. So what's the temperature of space now?
It's about 2.3 Kelvin.
Mm-hmm.
So,
right. Yeah. So it just keeps getting colder and colder and colder.
Yeah, it's not very warm.
So I'll pick up part of this other sequence of questions from Meorig. I hope I got that right. It has to do with energy loss and radiation. So when light travels from the sun to the Earth, are there any losses in energy of radiation? Well, if there's nothing in the way, no. Light will just travel. But if it runs into something, a dust particle, an electron, part of the solar wind, Earth's atmosphere, anything that gets in the way, then that light can scatter. That light can be absorbed. That light can be re-emitted. And so when that happens, when any of those scattering or absorption re-emission events occur, this can change the frequency, the wavelength of the light, hence the energy of the light. And in general, that does happen. And in fact, when you start looking at stars in the Milky Way, for example, that becomes a very big problem, because the light is effectively attenuated by the amount of dust. And when I say dust, I do mean actual dust, little particles about micron size or so, about like smoke particles, something like that. So in other words, the Milky Way is like full of like the smoke that damps the light. And so when people were first trying to estimate the size of the galaxy, they were very wrong, basically because you're living in a fog and you couldn't see very far before the light was completely reddened out of your wavelengths that you can see in. And so people estimated Milky Way is way too small and things along those lines. So if there's nothing in the way, yeah, light will just continually merrily traveling on without losing any energy. If it interacts with something, it will lose some energy. That's kind of the gist of that question. We'll cover light more next week when we actually cover light. So we will cover things like the Doppler shift, on how wavelengths can shift when objects are moving. We'll cover some of the basic properties of light, how the frequency is directly related to the energy, and so on. And telescopes. We'll cover telescopes next week. And speaking of telescopes, I think Teresa has a little presentation on some telescope stuff that she saw. So that's
yes.
Kind of a nice segue. Teresa, why don't you take it away on your telescopes?
All set up here. If I can.
No problem.
All right. Can you see it? Yes. Okay. All right, so like I mentioned before, I am an observational astronomer, so I get to use telescopes to do a lot of my research. But I kind of want to give a general background about some telescopes and some telescopes I've actually used. So now the two telescopes you see here and this first image, I actually never used. These were actually two telescopes that Galileo built and used to do his research. So as you might have learned in this course about some of the discoveries Galileo did with these very simple telescopes included discovering the 4 large moons of Jupiter, the Galilean moons, and found that the Venus had phases. And he did this with very simple, these telescopes using lenses. Okay, so the first telescopes used lenses like, you have for your eyeglasses, but more modern telescopes, which I'll talk about more, use mirrors. So lenses are refracting telescopes and mirrors are reflecting. Okay, so this picture I took over the summer. I had got to go to I was over in Florence, Italy for a conference, astronomy, and I decided to go to the Galileo Museum because as an astronomer, that was the one thing I had to do. And I got to see pictures and see all kinds of cool different telescopes and kind of gave me an idea of like how long it took to get to the modern telescopes we have now. Now, they kept building bigger and bigger ones, but the ones we have now kind of dwarf anything from the 1600s. All right, so next I'm going to show you some of the actual pictures I took from some of my observing experiences. So, is it actually? All right, hopefully working. Okay, so now you should see a couple of telescopes covered in, snow. So, which is bad for observing, right? So this is on Mount Graham in Arizona. I actually observed with both of these telescopes. In this instance where all the snow fell, I was actually helping a friend observe at the telescope on the left. It's actually called the Vatican Advanced Technology Telescope. It is supported by the Vatican. And so what's cool about this, not just the snow, is the experience of going to the Vatican telescope, because when it snows, you actually have to climb outside the side of the building, climb up a ladder, and go to the top of the building and shovel snow off of it. So, that's like a real astronomer, shoveling snow and then brushing snow off the dome so then you can observe later that night. So this is one of the, you know, kind of adventure parts of being an astronomer. Now, most astronomers actually do not go to telescopes. Even as an observational astronomer, I rarely get to go to a telescope. So just the way it is nowadays in astronomy. So this is the Vatican on the left. On the right is the Large Monocular Observatory. That's actually the telescope I use for most of my research. So it is near and dear to my heart because of that. Now, also, besides, you know, having to deal with, you know, being able to observe shoveling snow, we also, you know, had to deal with our car being snowed in. So, yes, that was also fun, digging out our car so we could get back down the mountain. And during our trip up the mountain, we actually kind of slid off the road a little bit and had to be pulled out by a snowplow. So, you know, astronomy can have fun adventures, you know. My next kind of telescopes are actually, I want to talk more about the Large Monocular Telescope. As I mentioned, this is the one I do most of my research with. It actually has why it's called the monocular telescope, because astronomers are very clever, is the fact that there's two 8.4 meter mirrors. Okay, so not just one, but there's two of them, and which is very unusual to have. And so I actually use them separately, but being that they're 8.4 meters, they're able to go very, very deep and into images with shorter exposures. So here we have a nice big picture of with the dome open, and we also have a close-up of the two mirrors, so you can see. All right. Next, I had to have a collage of a couple of telescopes I've got to use. Starting on the left, this tall telescope. Here you have a picture of me for scale, just to give you an idea, right? This is the on Kitt Peak. It's called the male 4 meter because the mirror is 4 meters in diameter. It is this big one. So there's a couple of pictures here in the mirror that shows you the kind of Kitt Peak, and this is the big one. This was built in the 70s, and if you go inside, you feel like you're in the 70s. You know, I always say that a lot of these telescopes that they'd be a good place to shoot a scary horror movie or something, because they're kind of creepy. So I use this one, and then there's also this other one on the top picture here below it. That's called the Bach. I've also gotten to use that one, which was it's a smaller 2 meter telescope. But also what's interesting about observing up here sometimes is the unusual problems you have to run into, including bears. So recently at Kitt Peak Observatory, they had issues with bears. And so people had a friend who went up there recently to observe, actually carry around bear spray with them. So things you don't think about when you're going into astronomy, bear problems. Okay. And then all the way on the right here, I have, this is another telescope called the MMT. It is on Mount Hopkins. Here we have a couple of nice pictures of it. And the history with this telescope is it actually used to be called the Multiple Mirror Telescope. That's why the MMT acronym. But they replaced the mirror for one giant mirror late 90s. So a lot of the, you'll notice a lot of acronyms. Astronomers like acronyms. Okay. So far, I've mostly just talked about reflecting optical telescopes, okay? So I have here kind of a picture of different diameters or sizes of the different telescopes. And as you notice, as we've gone through time, we keep making bigger and bigger and bigger telescopes, okay? So we're making bigger, basically, light buckets. You'll learn about this more when in the telescope section, but telescopes are light buckets. So the bigger you are, the more light you can collect quicker and go fainter faster. So that's the goal in astronomy nowadays, is to keep building bigger light buckets, bigger telescopes. And so like the Large Monocular Telescope is on here, but you'll also notice there's like 3 pretty big ones, the Giant Magellan Telescope, the 30 meter telescope, and the European Extremely Large Telescope, again, with the clever names by astronomers. Okay, so these are in development and should be hopefully ready in the 2020s to 2030s. But also coming with these bigger telescopes is they become very expensive, right? So most of these are no longer one country or institute making these, okay? They used to be a lot of times one institute or country would build telescopes, but now they're these international collaborations, okay? So to get funding to build them because they're so massive and expensive, which is really great because nowadays astronomy is international. You work with people all over the world, collaborate. So like I said before, so far I've only been, about telescopes across the world. I forgot about this. All right, so this kind of gives you an idea of where you can find, where we actually build telescopes in different parts of the world. And you notice they seem to be in a lot of the same areas. So you have in the US, in Arizona, where we have quite a few. Down in Chile, there's quite a few. South Africa, we have them. Australia. And part of it is because we like mountains for telescopes, and we like dry weather because that's best for observing, okay? Because clear skies, high altitude, great for observing. So there's certain sites in the world, including Hawaii, that are kind of the best places where they build, especially for optical near-infrared telescopes. All right. So far, I've only kind of I was talking about optical telescopes. So that's a very narrow range of the whole electromagnetic spectrum of wavelengths, right? So there's telescopes are developed for all to see different types of light. So another telescope I had to go visit as an astronomer was the Arecibo Radio Observatory down in Puerto Rico. Some of you might remember this from the movie GoldenEye or Contact, okay? So when I was there at Arecibo, I was there for a workshop. Here you can see me in the right, in front of the golf ball looking thing. That's actually where the instruments are. So this is the radio telescope is actually like a wire mesh. It's about 300 meters across. So up until recently, it was the largest single dish telescope in the world. And you couldn't actually move the dish. You actually move the golf ball at the top. And that is how you kind of move the kind of point in a way. And the instruments are in the golf ball. So I was lucky enough when I was there to I got to walk across this kind of behind me in the picture. There's a walkway up to it. And so I got to walk through it and actually go inside the golf ball. So that was pretty cool. And see the instruments. But the bad thing, though, is because it's a radio telescope, I couldn't use my cell phone. You have to have it turned off, okay? So I had no cell phone. There was no Wi-Fi. You actually plug in your computer to the internet. I know, mind blown. So, it was a cool experience for a week, but after a week, it was good to have my cell phone again. And it's a really, this telescope does a lot of cool science, especially for planetary. It does like radar work, actually works with other telescopes. It sends out signals, and then those signals are returned, and they can actually map asteroids. It was used to help with discovery of pulsars, so rotating fast neutron stars. All kinds of great science has come from this telescope. Now, again, until recently, it was the largest single dish telescope in the world, but it was recently topped by FAST. Okay, I forget what FAST stands for. It's actually 500 meters in diameter, just finished in the last year or so being built. It's another radio dish. It's built in China. Okay, and again, you want to build these telescopes where it's radio silent. Right, that's very important because your phone, your microwave, pretty much everything you have in your life sends out radio signals, which are bad for astronomy. Okay, very bad. They interfere when you're trying to make measurements. So these radio quiet zones they try to find, or you can see how it's kind of surrounded by mountains again to try to block out radio interference because it makes it harder to observe the signal you want to if there's other radio things like cell phones and TVs and all that kind of stuff. There's actually a place in the U.S. called the Radio Quiet Zone. It's in West Virginia. It's called Green Bay. And anyone who lives there is not allowed to have a cell phone, not allowed to have microwaves. They're not allowed, anything that has radio signal is not allowed. So some people like it. They choose to live there. So, all right. Okay, now the other issue for more optical telescopes is light pollution, right? Light pollution is a major, major issue. Here's a nice picture of the US, okay? And even here in Arizona, where we build a lot of telescopes, we have issues with Phoenix, right? It's a big light pollution in Tucson. And you can see the world at night as well. So finding places that are good to build telescopes becomes more and more difficult as we expand more and more to more remote places. And also for you, like I know some of you have been posting about doing the first outdoor activity about issues with light pollution or weather, right? So you can see the problem now. And if you've ever been to a dark site where you can really see the sky, because I grew up in the city and stuff, and when you really go outside the city lights, it's amazing how different it is. It's like a different world in a way at nighttime. So this is cool, just kind of a scale for those of you to see the difference, okay? So you have all the way on the right, kind of the excellent dark sky, okay? Like if you're in the US, maybe like going out to Yosemite or something, okay? And all the way to like the city, okay? So I'm used to more of a 6 or so, 7 where I live, right? And I teach astronomy classes to groups, and it's hard because there's so few stars to actually teach people with. So this is one thing as an astronomer we're trying to preserve is actually dark skies, right? So there's different organizations that support that, which is really cool. And a couple of more things. So far I've only been talking about telescopes that are here on the ground, because most of my research I've done and gone to actually telescopes you can go observe at are on the ground. But the issue with that is there's only a very narrow range of wavelengths of all the different types of wavelengths that you can see from the ground. So light comes in different types. You have gamma rays, X-rays, ultraviolet, infrared, radio, all different kind of light. And as an astronomer, we want to study all the light because it helps us better understand how things are, right? So if you just look at one wavelength, you're missing all this other information. So we want to study the whole electromagnetic spectrum, right? But the problem is, right, most of it's actually being blocked by our atmosphere, which is good. We don't want gamma rays hitting us. We don't want to become the Hulk, okay? So it's good that we have the atmosphere, but it's bad for when we're trying to observe it. So we have to actually build instruments specifically for these high energy and also for infrared, okay? So we actually build a lot of, maybe most of you probably heard of the Hubble Space Telescope, and that actually looks at wavelengths that we can see from the ground. But we built like the Spitzer Space Telescope, which helps us see these infrared, which are blocked. And we have Chandra, which is X-rays, okay, space telescope. We have a bunch of different ones and different gamma ray telescopes. Other things we do actually is also build balloons. So we don't necessarily have to get completely above the atmosphere. We just need to get high enough so we can reach those wavelengths of light. So we send actually balloon missions. A lot of those go out of Antarctica, which is pretty cool. Another cool mission that there is the SOFIA mission, which is a telescope on an airplane. So again, it gets high enough so we can see these long wavelengths of infrared. So I keep wanting to find a reason to get to go on SOFIA, because they actually, if you get observing time on this telescope, you can fly on the airplane, which I think would be really cool. So what they did is they actually cut a hole in the plane, all right, but it is all safe, right, and put a telescope. I'm not going to go into details, but it's a really cool thing if you want to look it up, the SOFIA Airborne Telescope. And then, of course, there's other wavelengths you can see from the ground are radio. But radio telescopes can be those big single discs like you saw with Arecibo, but they can also be arrays. So maybe you heard of the Very Large Array. There's the sub-millimeter array down in Chile called AMA. And these are a bunch of single dishes that work together, which helps us be able to see finer detail in faraway objects. So there's kind of a big variety of telescopes. Here's my last figure, highlights some of the different types of telescopes you can see in the ground and in space, and just show you that there's a lot more than just Hubble out there, which is one that we're using to explore all of space. And again, I mostly use ground-based optical telescopes, but these other ones help us understand all of the universe. All right, that's all I have.
Cool. I like the high energy ones. I like New Star. I like Chandra. Things that look in high energy bands. Yeah, and FAST. FAST stands for 500 meter aperture spherical telescope.
Again, very clever, right?
Fine. So if you look at it, it's a little bit more spherical than in shape than parabolic, so hence the spherical bit. Cool. Thank you, Teresa. Let's see. I don't see any more new questions on the discussion board. So I guess I will do a little spiel. Okay. So I'm going to talk about time. I'll just do my whole desktop. Okay. Is that showing up? Is that showing up? Give me a thumbs up if you see it. We're good? Okay, cool. Okay, I'm going to talk about time. And we covered a little bit about time at the start of the course. And we'll cover a little bit more detail here. So the passions of astronomy are no less profound because they are not noisy. This is a quote out of a John Steinbeck novel called The Short Reign of Pippin IV. It's one of the few comedy sarcasm pieces that Steinbeck wrote. And it's a story of a French countryman who's an astronomer. And as it turns out, he has some genetic material related to King Charlemagne. And so for short-term political purposes, he is elevated from gentleman astronomer in the country to the president of France. And he doesn't like it. And so as the cover of the book shows, he would often dress up as a commoner and escape out to the country on his motorbike to practice his astronomy. And hence the quote, one of the quotes there. Eventually, his reign doesn't last too long. It's the short reign of Pippin IV. So after a week or two, it becomes politically inexpedient, and he is removed as the president of France and returns to his passion and hobby of astronomy. It's a short book. It's a short read. Check it out. So time through the ages. So we're going to talk a little bit about time, how things got where they are. And as you will see, many, many vestiges of history are with us in time. So this is a nice little star clock and the Big Dipper there. So 'tis the season. So when humans start out, we're sort of agriculturally dependent. And so if you want to be agricultural dependent, that means knowing when it's time to plant, when it's time to harvest, and when is the first frost to put things away and get ready. That's all fine because that entire cycle is driven by the sun. So you just have to know where the sun is in its particular cycle. And there's lots of ancient monuments to be able to help, like Stonehenge, to help tell that time where the sun is doing. But as societies grow more complex, they want fixed dates for things like your birthday or the 4th of July for fireworks on the right, or when to pay your taxes. And so these are fixed dates. And this immediately introduces the difficulty of keeping the seasonal clock, which is what the sun says it is, and your human calendar clock, the time you want to impose upon the universe, right? So you have this sync, and if they get out of sync enough and you don't do anything about it, then eventually it'll be like the summertime season in winter, and that's no good. And so ever since society starts fixing dates, there's this immediate problem of keeping those two calendars, the seasonal and the man-made calendars, in sync. And so for reference, as we go along, the seasonal year is defined from one equinox to another equinox, fall equinox, spring equinox to spring equinox. And it's about 365 days, 5 hours, 48 minutes, 46 seconds, or roughly 365.24 days. And we'll come back to that. And of course, this is a famous Dali painting on the persistence of memory and melting clocks. And what do clocks mean? Seasonal or calendar clocks. So as societies move on and they start having their fixed dates, the yearly calendars were often based, so this is like the beginning of the year, were often based on one summer solstice to another summer solstice, or when a particular star first rises with the sun, the heliacal rising as it said. So the picture here is showing the heliacal rising of Sirius, which is in the constellation Canis Major. And so the Egyptians used Sirius, which is the brightest star in the night sky, when it rose in early July, when the Nile was in flood. And with an economy based on the Nile floods, this was an important time because we're agriculturally based here. And so the heliacal rising of Sirius was the most important and hence the very first day of the year. So what we call January 1, and we'll get to that in a bit, was originally in the summer with the Egyptians. This is when they started the beginning of the year with the heliacal rising of Sirius in Canis Major. So because Sirius is in the constellation Canis Major, which is Canis being a dog, it is often called the dog star. And it is from the Egyptian use of the heliacal rising of Sirius in early July. That's where we get the phrase, the dog days of summer. And so that phrase goes back several thousand years. Okay, so a year's kind of a long time, and so naturally you may want to break that up into smaller chunks of time. And so how do you mark time intervals within a year? So the first marker was the moon, which is the root word of month. So month and moon are intimately related. But there are two obstacles related to using the moon to subdivide the year. And the image here is the Aztec calendar stone, and they had a lunar-based subdivision of the year, and this is their calendar on their mobile device. Okay. The first obstacle is that the lunar month is not constant. It varies around. It moves around between about 29 and 30 days. And this variance is due to using what's called the synodic period rather than the sidereal period, or the sidereal period, as I will say. So the synodic period is what you see. It's easy to observe. It's the time between, for example, full moon to full moon. So this is between identical sun, earth, and moon alignments. It's easily observable, but it's not very useful because it's not constant. On the other hand, you have the real period, the sidereal period, like sidereal, so it's kind of buried in the word. And this is the time between star, earth, and object alignments. This is the real period. This is the period that you would put in like Kepler's third law, either in Kepler's form or Newton's form, but it's harder to observe. It's not as straightforward to observe. And let me walk a little bit why there is a difference between those two. So I'm going to start off this 4-frame movie with everything in a line. So I've got the sun, I've got the earth, I got the moon, and I have a distant star, and everybody's lined up. And I'm going to start the clock running at this point. Okay, so now time goes on. The moon goes around the earth, so to speak, and then the earth goes around its orbit around the sun. And so after a certain amount of time, you will have an identical earth, moon, star alignment. This is the real period. This is the sidereal period, and this is 27.322 days. That's why it's got so many decimal points after it, because it's the real thing, and you can measure it. But the moon is not full, okay? So this is the synodic period. If you want to get to a full moon, you have to wait a little bit. The moon has to go a little bit farther so that it's opposite the sun. And so that's called the synodic period, when it goes full moon to full moon, and that varies between 29 and 30 days. It varies because the orbit of the Earth around the sun is not exactly a circle, it's slightly elliptical. And so sometimes the Earth moves a little faster, sometimes it moves a little slower, and this is, of course, a topic of this week's lecture material. Okay, so two different periods, one of them real, one of them easy to observe. And of course, the ancients are using the ones you can easily observe, and that creates a little bit of a problem. The other problem is that the year cannot easily be divided, so sort of by the average lunar month of 29.5 days. 12 lunar months is about 11 days too short, 13 lunar months is about 19 days too long. And so if you mark your time with the moon, sooner or later your calendar is going to get out of sync with the seasons. This repeating problem that's gone on for several thousand years. Okay. And so many cultures got around this conflict by inserting an extra 13 months every few years so that you could resync your seasonal and calendar years would stay together. Okay. And it is from this that we get a whole lot of words associated with using the moon as a timepiece. So for example, it was kind of accepted practice in Babylon. And for about a month after a wedding, the bride's father would supply his new son-in-law with all the mead he could drink. And so mead is a beer. It's a honey beer. You can still buy honey beer, mead. And so this period after the marriage, that whole month where he could get all the beer he could drink was called the honey month, or what we have shortened today to call the honeymoon. Okay, so our use of the word honeymoon dates back several thousand years to using the moon as a calendar device. And as Bill talked about a little bit earlier, we have blue moons. We got one coming up on the 31st of January. We have lunatic. That's just a general word for luna, la luna, the lunatic. We have wet moons, harvest moons, super moons, lots of moon names that you can look up on the web. Okay. So time goes on, and the Egyptians are the ones who sort of gave up on using the moon to mark time within a year, and they took a more radical approach. They are the ones that divided the year into 12 months, and so this is the origin of our 12-month year, although with a few twists, as we will see. So they divided the year into 12 months of 30 days each for a total of 360 days. And even the Egyptians knew that the year is not 360 days. It's a little bit longer than that. So at the end of every year, they added 5 days for an approximation of 365 days. Of course, they know it was not exactly 365 days either. And so extra days were randomly inserted to keep the seasonal and the calendar year clocks synchronized. Time goes on. The Romans rise to power. And originally, the Romans had a really messy calendar. The calendar was 10 months long, with March being the first month of the calendar years. Extra days were inserted at random at different locations within the Roman empires to keep the seasonal and calendar years aligned. The image there is an example of a Roman calendar at one particular location, giving when these extra days were to be randomly inserted. The Roman calendar is still with us in many ways. So for example, September, October, November, December, those months' names are from being the 7th, 8th, 9th, and 10th month of the Roman calendar. And if you speak Spanish or any related languages like that, and you count to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 7, 8, 9, 10. That's where we get those. But of course, they're not the 7th, 8th, 9th, and 10th months now. They've been shifted a little bit. So they're sort of like completely misnamed in our calendar year these days. So with the Roman Empire scattered around and people adding random days at various times, it was Julius Caesar who decided to implement some order in the calendar across the empire. And so a year before his death, Julius instituted a new calendar. There were going to be 12 almost equal months. March was still going to be the first, totaling 365 days. But now we were going to get organized in when we add these extra days. So every 4th year, or leap year, one extra day was added at the end of the year. And so this gave an average year of 365.25 days, which is pretty close to the real one, but not quite. Okay. And Julius Caesar liked his new calendar so much that he decided to name a month after himself. And so this is where we get to July. July stands for Julius Caesar and his calendar. And politics and money kind of go together, right? There's a little money in politics. And so Julius had a benefactor, and they were known as the Juno family. They were sort of the business titans of their day. And he honored them by giving them the name of one of the months in his new calendar. So from the Juno family is where we get June. Okay, so June, July, Juno, Julius Caesar. And of course, now the pattern's set, right? So every emperor past Julius Caesar decides to rename one of the months for himself. Fortunately, this doesn't stick except for one of them. One of them that stuck was Augustus Caesar. So this was Julius's grandson. And is from Augustus Caesar is where we get August from Augustus Caesar. So June, July, August, these names of the month are from the Roman emperors and the business titans of their day. So 365.25 is close, okay? It's about 11 minutes too long, or about 1 day in 130 years, or about 1 week after 1,000 years. Who's going to worry about that? Well, guess what? Time goes on. And so by 1582, with no adjustments to the calendar, the seasonal and calendar years were about 10 days out of sync. And this is quite noticeable. And so it was then in 1582 that Pope Gregory introduced the Gregorian calendar. And the first thing you have to do is synchronize the seasonal and calendar years. So take a close look at this calendar in October of 1582. October 1, 2, 3, 4, 15. Oh no. And so this just chopping out 10 days of the calendar to resync everything caused, as you might imagine, a lot of social chaos. What if my birthday was in there? Do I still get paid during that time? Do I have to pay taxes during then? All kinds of questions of this sort. Near riots in the streets of cutting out 10 days because of the uncertainty that it introduced. Nevertheless, it stuck. Those 10 days were chopped up to resync the calendars. And so we needed yet something a little bit more sophisticated. So one, because now the Catholic Church is now in power, and we can't have March being the first anymore. So the first thing is to shift the origin point. So this is when January 1st is made the beginning of the year. It's where we get this. It's from Pope Gregory. And so every 4 years, just like the Romans, an extra date is added to February. So far, nothing's changed. All you've done is shift the origin point. The rate at which the clock moves hasn't changed at all. But now he implements a new rule that century years that are divisible by 400 are also leap years. So things like 1700, 1800, 1900, these are not evenly divisible by 400, so they are not leap years. But things like 1600, Y2K, which we just went by, that's evenly divisible by 400. And so those are also leap years, and we had an extra day. The Gregorian calendar is 38 seconds too short, or 1 day in 2200 years. So we've been dealing with this seasonal and calendar sync problem for a couple thousand years. And what are we going to do? Are we going to wait another 2200 years before they get out of sync again and go through some upheaval and apply another correction factor? No, we don't do that anymore. And so these days, 1 second is added to the seasonal clock. And I just remember Bill's question from the last time. 1 second is added to the calendar clock at midnight on June 30th or December 31st. And maybe you've heard that on the radio or seen it on television or on the internet. When all of a sudden they tell you, they're going to add a second at midnight to resync the clocks. And you might go, what the heck? Why do we do that? And again, it's to sync the seasonal and calendar clocks and not run into this problem of waiting till the error builds up to the point where it gets silly and then you have to make a major change. So 1 second at midnight is probably not going to perturb anyone too much. So the calendar clock is the time we want. It's the man clock. And that's set by using a network of atomic clocks. And the seasonal clock, what the sun says, what is actually what the rotation of the Earth is. That's done by the International Rotation Service in this very nondescript brick building with metal bars over the windows. They are responsible for measuring the Earth's rotation, hence the period of the day. Okay, so that's our modern year. We covered this a little bit in the course. How come there's 7 days in a week? There are 7 days in a week because to the ancients, there were only 7 objects that changed their position on the celestial sphere. The sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. And so that's 7, and each one of them got their own special day. And so our names for the 7 days come from the Norse Celtics. We have Sunday, that one's kind of obvious. Moon Day, Tuesday for Mars, Woden Day, Mercury, Thor Day, Thursday, Jupiter Day, Freya, the only female in the group, Venus Day, and then the obvious Saturn Day. So that's a little bit on the days of the week. How about time zones? Where did time zones come from? Who implemented time zones? So time zones came in basically because of the trains. When you know, as long as you're traveling slow, it doesn't really matter what the time differences are. But once you start speeding things up and you move into trains, it was really hard to write a schedule because it wasn't clear what time did you mean. Because every place has its own local noon. Were you talking about the local time? Are you talking about New York time or LA time? And so it was confusing to passengers and to business. So basically, for business purposes, it was the railroads who established the time zones in the U.S. And so all cities within that band were given the same time. That's not true astronomically. Each local place has its local noon, but this made it a lot easier for commerce. And so that was a fantastic system. And of course, we went from trains to airplanes. And so by about 1918 is when Congress made them official. The time zones were official. And then later in about 1923, the forerunner of the United Nations, whose name I forget right at the moment, implemented it worldwide. And so it was basically travel that implemented time zones. The time zones basically more or less follow lines of constant longitude. So we have a thread going in the discussion board on longitude and times in the northern southern hemisphere. But of course, they don't strictly follow longitude because there's geopolitical realities. And so as you can look at this map, sometimes they do some pretty crazy stuff along different regions. But that's basically where we get time zones from, is travel. And that's what I had to say about clocks and our ability to keep time according to Earth's rotation and the sun through the ages. Okay, thanks. Okay, stop. And I still remember your question from last week or last time, Bill. And okay, now I will look it up.
I'll let you off this time.
Thank you. I will get an answer to that. Okay, how are we doing on time? We have about 7 minutes, so maybe we'll see if we got any new questions. Let's see. Nope, I don't see any new questions. Okay, we've been going about an hour. That'll do for this time. So thank you so much for joining. And we have a second YouTube event in about 5 weeks. Instead of being at 0500 UTC, it'll be at 1700 UTC. So we kind of get the other half of the globe in our second YouTube. Okay. If you have any questions or anything, please ask them in the discussion boards, and Teresa, Bill, or I will endeavor to answer them. All right. That'll do. Bill, thank you. Teresa, thank you so much for joining.
Mm-hmm. All right. See you, everyone.
All right. See you. Bye.
Bye.